Qual que é aqui? Ah, tá. Esse aqui é o...
Berlim.
Tá. Tá bom.
Well, good morning, everyone. Now, this work was made jointly with my advisors from PUC, Alexandre Stich and Davi Valadão. And first of all, I would like to discuss what is a time-consistent policy. Now, the definition found in today's literature is that a policy is time-consistent only if and only if future planning decisions are actually going to be implemented. So suppose that we are at period 0, we have an implemented decisions and a couple of planning decisions for future realizations of a given uncertainty. And then, as we move on in time, one of these uncertainties will occur, and we'll have a new implemented decision for that scenario that is related to this past decision that we made in period 0. Now, in the context of dynamic stochastic programming, suppose that we have, yet again, a scenario tree, and the decision maker has to define a multi-stage problem to be solved at node A at period 1, and two multi-stage problems to be solved at node B and node C, depending on which of the uncertainties actually occur. And he expects to obtain an implemented decision and a planned policy for the future. Now, first, the decision maker will solve the problem P1 to obtain an implemented decision for node A, XA, and planned decisions for each of the possible realizations of the uncertainty in the future, YB and YC. Now, suppose that we're given uncertainty realization B. Now the decision maker will solve problem P2B to obtain an implemented decision XB. Now suppose that, now let's go back and let's suppose that we're given uncertainty realization C. So the decision maker solves problem P2C in order to obtain the implemented decision XC. Now, time consistency requires that the implemented decisions XB and XC are equal to the planned decisions YB and YC. So far, this has been investigated in literature in the context of nonlinear time inconsistency due to nonlinearity on risk measures. And here we're trying to, we are aiming at characterizing modeling simplifications in the planning step as also as a possible source of time inconsistency. That is, the model used in the planning step is different from the model used in the implementation step. Now, as widely used, the stochastic dual dynamic programming, the STDP, for in the context of hydrothermal planning, we're using it here as well. And in this case, our uncertainties are inflow scenarios, and our planning problem for a given sampled scenario and period T consists of minimizing the operation cost, an equation that ensures system power conservativeness of power flow, and a constraint that ensures water balance. You know, this is our state transition equation. And set xt is supposed to contain all of the possible constraints and that might go in the model as well. And finally, we have our recourse function that is the expected cost of the future operation. Now, the main idea of the STDP method is to replace the recourse function by an approximation by a set of cuts that has this equation here. They have this equation here. And in the forward step, in our case, a single scenario path is sampled from our scenario tree. And the period for each, the problem for each period is solved using the sampled scenario. And then at the end of this step, we have a sequence of trial decisions to be used in the backward step. In the backward step, we start at the last period of the planning horizon, and we solve using that trial state that came from the forward step. We solve the problem for each period, for each scenario in that period to obtain the cost, the operation cost for that scenario and a dual variable that is associated with the state transition equation. Then we take the expected value of both this cost and the dual variable, and we can fit them in the Kurtz equation to form a new approximation for the recourse function. Now, this procedure has to stop eventually, and we propose a stopping criterion that is based on both lower bound and upper bound stabilization. So firstly, we run 1,000 iterations of the SDP method, and by means of a simulation procedure, we obtain an estimator of the total operation cost. There's called the upper bound, and at lower bound there is the objective value of the first period problem. Now we want to check if, now we repeat this evaluation step every 100 iterations, and we want to check if the difference between two consecutive lower bounds in the evaluation step is less than 1%, and to check if these two consecutive upper bounds come from a population with the same mean. You do that by a means of a hypothesis test. If we observe both these situations here, we stop the algorithm. Now, in this framework, what in practice, we have a planning model that the decision maker, the system operator, is going to run using the SDP method to obtain a planning policy, and then there will be an implementation model that the decision maker, the system operator, will couple the recourse function that came from the planning model into the implementation model to actually implement the system, to actually take the decision. Now, the set xt here in the implementation model is supposed to be much more detailed than it has much more constraints, more operation constraints than the set in the planning model has, which is similar to what happens in practice. Now, so suppose that we are at a period t, the system operator will run the SDP method using a planning model that is simplified, so set x is simplified, to obtain a planning policy and a recourse function. Then we're supposing here, for the sake of the effects that we're trying to show, that this recourse function is optimistic toward future outcomes. Now, so when the system operator couples this recourse function that came from a simplified model into an implementation model that has a detailed set to implement the system, if this recourse function is optimistic towards the future, what might happen is that our implemented policy, for example, for system reservoirs for storage energy in the system, might deviate from the planned policy, and we might end up with less energy in the system than we thought we would, leading up to higher operation costs. Now, this procedure is repeated for the next period. The decision maker, the system planner, will run the SDP algorithm with a simplified model to plan the system to obtain a new recourse function that will be coupled again into an implementation model to take a new decision, new implementation decision. Now, supposing again that this is optimistic, what could happen is that we could have less water than we thought again, and higher operation costs than our planning models could see. Now, what is the problem with this procedure is that we don't actually know what's going to be the uncertainty realization by the time that we are actually implementing the system. So the idea here is to simulate this procedure for many scenario paths, for many sampled scenario paths. And in the end, we have a set of implemented decisions. Now, to sum this up, we have this algorithm, the SDP method extended to the holding horizon scheme. Firstly, we sample these M scenario paths, M inflow paths, to be used in the implementation step. And then we set the t equals 1, the first period, and we set for each of these paths an initial condition, an initial stored energy in the system. Then for each of these paths, we repeat what I just explained. We run the STDP, we converge the STDP algorithm with a simplified model to plan it. And then we have a new recourse function that we're going to couple into an implementation model to obtain a new set of implementation decisions that we'll store in set P. Then we move on in time, and our initial conditions for the next time will be exactly how the final stored energy for the problem that I just run, for the T that I just run. So we repeat that until the end of the planning horizon. Now, this procedure can be really highly time-consuming because we are converging the STDP algorithm time and time again. So it could lead to unreasonable computational time. So what we propose is a fast algorithm in which, in the forward step, it's an adaptation of the STDP method, in which in the forward step we are running it with a with a detailed model to actually implement the system, to simulate the implementation of the system. But in the backward step, we use a simplified model to actually construct approximations for the recourse functions. So what you're doing is that we are implementing the system with a detailed model, such as what we're doing in practice, but using a recourse function that came from a simplified model. So we run many tests to compare whether these two algorithms, whether if this algorithm is really a good approximation for the former, and all of the policies that they built, they matched it really well. So what is the time inconsistency gap? This gap is the gap that arises from is the difference between the expected cost given by this time inconsistent implemented policy that is evaluated by the STDP algorithm running different models for the forward and backward steps. Is the difference between this expected cost and the expected cost of what would be the cost given by a planning model as it's done. We're using simplified models for both the forward and backward steps of the STDP algorithm. Now, there exists the possibility that this gap here is due to a sampling error. To check that, we run a hypothesis test to check if the true population mean of this sample is equal to the true population mean of this sample. If 0 is not on the gap interval, then we reject the new hypothesis and we claim that the gap is statistically significant. Now, as a first example of a possible time inconsistent source in hydrothermal planning, we suppose that neglecting the Kirchhoff's voltage law. That is, in this case, besides the power flow conservativeness and the water balance, the state transition that I've already mentioned, we also have a set XS, a simplified model that contains only bounds for decision variables. And a detailed model, the model that is actually going to be used to implement the system, contain not only the bounds for these variables, but also the Kirchhoff's voltage law. Now, running this procedure for a simple free-bus system that contains a large hydro generator and a couple of thermal generators in which the thermal generation that is on the same bus as the demand is much more expensive than the other one, we arrive at a time inconsistency gap of 1,074,000. And you see that 0 is not on the gap confidence interval, so we claim that this gap is statistically significant. And to observe the policy built by the algorithm, in red here is represented the policy built by this time inconsistent procedure that is running the STDP algorithm with different models for forward and backward steps. Now, the line is equivalent to the expected storage energy in the system, and also the confidence interval, the 95% confidence interval is also shown here. And in black with confidence interval gray, we have, just for comparison purpose, we have also the policy built by the STDP algorithm running with models, with detailed models, with implementation models for both the forward and backward steps. And we see that in the inconsistent policy, the stored energy is is below than it is in the consistent policy. And in addition, the reservoir is constantly being depleted, especially in dry seasons. Now, this leads the expensive thermal generator to be constantly being dispatched, especially in dry seasons, in the inconsistent policy, whilst there is no dispatch from this unit in the consistent policy. And a direct consequence of this is that spot prices starts to peak in the consistent policy, especially in the dry seasons as well. Whilst in the consistent policy, they're much more well behaved, around 20. Now, as a second example of a second possible source of time inconsistency, we consider neglecting security criteria. So in this case, we have a set of pre-contingent constraints and a set of post-contingent constraints. In the post-contingent constraints, we also have a power flow conservativeness constraint for each contingent state C in a set of contingent states C, and we are also allowing the possibility of power system imbalance by means of these phi variables here. And you're penalizing the worst case by means of the worst case power system imbalance. We're penalizing it by means of this auxiliary variable delta in the objective function. We also have a state transition equation that ensures water balance for each contingency state C, Kirchhoff's second voltage law, and a couple of constraints that ensures that there is a limit how much can post-contingent decisions for thermal generation and the water and the energy discharge from hydros can vary from between pre-contingency and post-contingency decisions. And finally, matrix Z models exactly the security criteria that you're using. For instance, in this matrix here, for a given transmission line L in a contingent state C, the corresponding element on the matrix is 1 if the line is available and 0 if the line is unavailable. Now, for this case, our implementation model is both the pre-contingency and post-contingency constraints, while the planning model, the simplified model, is only the pre-contingency constraints. Now, running, it's on the same system, but at the time considering a security criteria of n-1 only in transmission lines, we end up with a gap, with an inconsistency gap that is about 10 times as it was on the case in which only the Kirchhoff's voltage law was neglected and 0 is not in the confidence interval, so the gap is statistically significant. And again, we see that the inconsistent policy for the stored energy is always below the consistent policy, and the reservoir is again constantly being depleted. Thermal generation for the inconsistent policy is again always peaking, especially in dry seasons. And we see that there is load shedding. In this case, in the inconsistent policy, there is load shedding, whilst in the consistent policy, there is no load shedding. And this leads to the spot price to be, again, constantly peaking in the dry season in the inconsistent policy. Now, quanto tempo tem?
Vai precisar 3 minutos.
Tá. It's interesting to analyze these results against some states that were actually implemented in the Brazilian system. Now, if we analyze the stored energy in the Brazilian Southeast system in the year of 2012, we notice that in that year, we had a historical maximum compared to the past decade, and it depleted faster, and we ended up in a historical minimum compared to the same decade. Now, what's interesting, what's intriguing is that the inflow in that year is not amongst the worst case scenarios in our historic. And what's interesting is that different from the usual, security criteria such as the N-2, a tight security criteria, was constantly being implemented in the system. And whenever there was a storm in a critical area of the system, the security criteria was reinforced, and even tighter security criteria such as the N-3 was implemented. Now, Obviously, we're not with this simply case, it's a free bus case system. We're not trying to conclude anything. We're just trying to bring the attention to these negative side effects and to create a new analysis tool that allow us to check the negative effects and its costs that might arise from time inconsistent policies due to modeling simplifications in the context of hydrothermal power systems operations. So, thank you very much.
Okay.